entropy is expressed in bits. And what we know, of course, for a fair-sided dice is that the probability that the outcome takes on a particular value k is just 1 over 6 for k being between 1 and 6. So if we now just take the equation for the entropy in the discrete case, and so we know that h of x is the sum over all x element of the possible set of outcomes of p of x times the logarithm of p of x, so that would be 1/6 times the logarithm, and we choose logarithm to the base 2 of 1/6. And, sorry, minus, of course. And that is simply minus the summation. It's just a multiplication with a factor of 6 because it's the same for all of the possible outcomes. So 6 times 1 over 6 times minus the logarithm of 6, because the logarithm of 1 over 6 is minus the logarithm of 6. Right? And so this is logarithm to base 2 of 6 bits. So that was question A. And when it now comes to questions B and C, we can argue very simply that the different throws of the dice are independent of each other. And we'll see that in case C as a general rule, that when we have independent realizations of the different throws in a series, then we're just adding up the entropy. And so in the case of the of two throws x and y, that just tells us that, well, we have 36 possible outcomes, and any possible combination between the two. Of course, we're looking here at ordered pairs, so it is really just 6 to the power of 2, and the probability for each of them is exactly 1 over 36. So that means that, very similar to here, we're now saying that, well, it's the sum over all pairs, 1 over 36 times the logarithm of 1 over 36. So that's again, so let me write it out explicitly, xy is 36 times 1 over 36 times the logarithm to base 2 of 36. And that is the answer here. And when we're going to item C, right, so generally speaking, we can say that the probability of x being x1 up to xn being small xn is just 1 over 6 to the power of n. And so that means our entropy of that whole series is minus the sum over all outcomes of 1 over 6 to the power of n times the logarithm of 1 over 6 to the power of n, which is just n times the logarithm to the base of 2. Logarithm to the base of 2 of 6 bits. And so entropy just gets multiplied with the number of realizations. Okay, so that was that. Now, a further comment concerning the last lecture. I realized afterwards that I made a bit of a mess in the writing down of both the solution of the example and then for the cross entropy, because I didn't have I forgot this one page of notes that I had with me. So I scanned a proper write-up and uploaded it to Whitespace. So if you're wondering, or if you're going through that material again, please look at those notes to give you additional information or cleaned up information, which might be easier to read. Now, I am going to write something that looks a little bit funny here, because for people watching this at home, one of the things that turned out in the quiz that I set out is that some people actually don't listen to the lecture; they only read the notes. And so that's why I'm writing it down here, so that they actually tune in here. And let me immediately tell you, only reading the notes, not listening to the lecture, is something that I would strongly discourage in your own interest. And the notes that I'm writing down here are mostly about the equations that serve basically as for you to hold on to what is the development of the things. But obviously, they are not a verbatim transcript of all the things that I say. There's a lot of what I'm actually speaking and giving explanations that never are written down in the notes. So what you need to absorb and what you need as the basis for whatever is being asked in the homeworks, in the exams, and so on, is the full material of everything that I say, not only the things that I'm writing down. And so I hope that clarifies that point a little bit. Now, continuing on the question of the quiz, so first of all, thanks to everybody who filled it out up to now. If you haven't done it yet, please continue to do so. I will be looking at it again in the during the weekend, but just by late last night, we had 14 answers, so I'm just going to say a few things based on what was mentioned at that time. And so there are some things where I will just have to explain to you why I cannot change it for the last part of the lecture, but there are other things that were mentioned as problems that you encounter or suggestions that I thought, okay, those are good points. I will try to take them into account for the last issues, or for the last lectures and then for the finals. So let me go through things one by one. The first, I guess, is a thing that I cannot change, where the comment was, well, there is so much material in every lecture, and that is simply established as the required curriculum by the curriculum committee. And as you know, 503 is the prerequisite for almost all other master's courses or classes that you are encountering in EE, and so you need to be familiar with the different aspects because you will need them later on in those other courses. So the amount of the material we are facing is not a variable in this whole thing. There's a little bit of possibility for adjustment, and actually, as I already indicated, I will probably have to skip over the Markov chains because we're simply going to run out of time. But that's pretty much the extent of that. The second point was that some people ran into time problems at the midterms, just saying that, well, if I had only had more time, I could have solved more of the problems. We might adjust the number of exercises that will be asked in the finals down from 8 maybe by 1 or 2 to give a little bit more time. It didn't seem to be the main problem for most people, but if you are knowledgeable and would normally be able to solve it, then, well, it doesn't make sense to make the time here as the main stumbling stone. There was also an issue about being able to remember equations, and while I'm not going to allow a free-flowing cheat sheet for reasons that I mentioned before, right? Because if you need to remember the equations, you hopefully at the time will also think about, well, how do I actually apply them? And it's often turns out to be a disservice to allow the cheat sheet, because you're looking then at the exam through all of the possible equations, think how could I apply them without really thinking about it beforehand, and this often results in worse outcomes than if you're just trying to memorize things. However, I do realize that given the large amount of material that's accumulated now through midterms 1 and 2, the total number of equations you're supposed to remember at once is becoming somewhat large. So the solution that I figured out for that is that the full equation sheet that I had uploaded, right, not only the things that are marked in red there, will be appended to the exercise book for the finals. Now, this is only going to cover the equations for midterms 1 and 2. Right? The point is that you don't have to overload your mind with the equations you've already memorized in the past, in the expectation that, oh, maybe I'm going to need that for the finals, but that you can actually focus on the equations, on the material that is the main focus of the finals. And so just also to solve any potential lingering questions you might have about the material on the finals, very similar to the midterms, theoretically, the whole material of the lecture is going to be on the test, but of course the focus is going to be on the material that we had since the second midterm. And so these are some modifications that I'm going to make to maybe ease your life a little bit in the preparation, and to focus on the things that are really essential for the finals. Now, that being said, I also wanted to give a little bit more suggestions about how to prepare for the finals. And one of the biggest, by the way, one mistake I made in the poll was that I didn't ask whether the people who filled this out were doing better or worse on average, right? Because somebody might have clicked on, oh, I did this and this to prepare for the midterms, and maybe they got 98%, and so that, of course, would have been useful to know of who actually had a successful preparation way. But anyway, that ship has sailed, so let me just go with the general statistics of how people mostly prepare and what my recommendation is. So the biggest challenge really seems to be to transfer the knowledge of the theory into actually writing down the fundamental equations in the exam of, okay, this is the mathematical formulation that I have to solve. And there were, of course, a number of requests to increase the number of examples that we're doing in the course. I actually had already all the material prepared for the next 3-4 lectures. Based on this, I've thrown in a number of additional examples here, so to maybe help you along a little bit. But it will never be enough in that sense to fully prepare you for the exam. And I wanted to stress one thing that's just so incredibly important, namely that you actively solve examples. Right? I know I didn't put it among the quiz question on how you prepare for the midterms, but just passively taking in the solutions from the lectures, from the discussion sessions, and so on, is not enough. Right? You have to actually go out and yourself solve examples. Right? The homeworks, to a certain degree, are forcing you to do that. The quizzes, I'm trying to make you do this a little bit as well. I know the people that are here in the lecture in person are doing that, and I don't know whether the people at home are doing that as well, or whether they are just fast-forwarding to when I present the solution. If the latter, then I would very strongly recommend to you that you actually hit the pause button, try to solve the problem yourself, and then listen to the solution of whether you've done it. And remember, the quizzes are a very important way for you to verify of did you actually have, did you understand the material from the last lecture or not. And if you have problems solving the quiz, then you're probably going to have problems solving a similar problem at the finals, because you're in the same situation and you have to come up with your own solution. Also, very important is that you try and use exercises that are beyond the homework and the things we do here in lecture and discussion session. And my strong recommendation there really is to look at the exercises, the end of chapter exercises in Yates, because the authors have actually published the solutions quite officially for all the odd numbered examples. So there are, I think, somewhere around 400, 500 examples in Yates at the end of chapter. Half of them, the solutions are there. Now, the key thing here is don't just look at the problem statement and then the solution, but look at the problem statement and try to solve it yourself. And it is the biggest misconception that, oh, when I hear enough solution methods on how to solve these examples, I know how to do it when I'm in an exam. And this is not the case for 99.9% of all people. To give a slightly imperfect analogy, and for those of you who are playing piano, and you can read the score of a piano concerto, but to just sit down and then say, okay, and now I'm going to play it in the orchestra, with the orchestra, in a public concert, is probably not something that you would do. Arthur Rubinstein could do that, and he actually once did that. But unless you happen to be Arthur Rubinstein and you're one of the 1 million other piano players in the world, you need to practice the whole thing about 100 times before you can go out and play it in a concert. Right? Similar thing here. There might be a few people who actually have the talent of just absorbing, okay, these are the solutions, I never have to do it actively, and they are able at the exams to immediately solve all these complex exercises that you have. But you have a pretty good guideline right now from the 2 midterms. And if that recipe hasn't worked for you in the midterms, then very likely it's not going to work for you in the finals either. And so I noticed when I looked at the grades of midterm 1 and midterm 2, and there were some people who actually, from the first to the second midterm, their points went down considerably. There were others where the points jumped quite a bit. So in both of those cases, you probably know what was the difference between your preparation for the first and the second one, and obviously you can draw your lessons from it. The ones that went from 30 points to 80 points, well, keep doing what you're doing for the second midterm. And if it went the other way around for you, think back to what did you do different in midterm 1 and try to find that recipe again. But for most people, they pretty much stayed the same. The ones who were at 90 stayed mostly at 90. The ones who were considerably below average tended to stay below average. So in those cases, where you were below average, you have to rethink, okay, obviously what I did didn't quite work for part 1 and 2. What do I need to change here? And I think really the most critical thing is just practice, practice, practice more of these things. And as I said, you have to be active. You cannot just try to get the material by osmosis and by passive consumption of the material here. The last thing I want to stress is if you are unclear about concepts, and I guess that happens frequently, please make use of the office hours. And I consciously structure them in a way, first of all, that they are at different times. So if somebody, for example, on Thursdays cannot make it in the time between 10 and 11, well, on Tuesdays they're in the afternoon, so hopefully there is no conflict on both of those times that are being offered. And I also know that since a lot of people are watching this remotely, it might not be easy for them to actually come to the office, which is completely fine with me. That's why I set up a Zoom link that you can ask the questions remotely. But this is the service for you to get additional explanations of what we've been doing in the lecture, and I do encourage you to use that. It's of course already pretty late in the semester, in the sense that since everything builds on everything before, it's good to clear up your questions before they have ripple effects later on, but better late than never. And so please feel free to make use of that. Okay, so those are a couple of suggestions on what to do for the finals, steps that I'm taking to make things a little bit easier for you. Any questions on that matter? Okay, if not, then let's move on to the new material for today. So last time we started to discuss about random processes. We were saying these are basically families of random variables that can usually be interpreted as a sort of time series of random developments. And we were saying that we now have to distinguish between, let's say, a sample path, right, where we're just seeing different random realizations over time. And so this might be one sample path, this might be a different sample path. If we're taking sort of a cut of, or we consider the realizations at a particular time t, we're just getting different realizations here of one random variable, which we're calling xt, or if it's time discrete, we're saying it would be an xn. And so we still have different random realizations here. But then if we're looking at one particular sample path, it's basically the particular evolution that, let's say, a particle going through a diffusing liquid, like Brownian motion, is taking, or that the received signal power in a randomly fading channel is taking, and so on. And so the distinction between sample path and the different realizations over time is something that is very important. We might have an integral over time to characterize certain quantities. I think this might very often be just an integral from minus t to t, with t going to infinity, to describe certain characteristics of the sample path. And on the other hand, we might have the expectation over the ensemble, right, which means that we are looking at the expectation of the random variables at different times, at one particular time. And for another time, we again say, well, what's the expectation over the random variable at that particular time? So this is, again, very important to keep apart conceptually. And the properties of a sample path averaged over time might or might not coincide with the properties of the random variable averaged over the expectation. If they are identical, then we're calling this an ergodic process. But there is no guarantee that a random process is ergodic. You have to verify that in every single case, and you have to consider it. We will later on get to the concept of stationarity, and we will see that ergodicity automatically implies stationarity in a system. But for now, let's just say we need to make this fundamental distinction between expectation or average over time and expectation over ensemble. Okay, so this is how far the textbooks are usually going, because this is what you're doing in theoretical probability. Now, the thing gets a little bit more complicated when you're actually doing experiments. And I'm taking again the example of a wireless propagation channel, because that's just from my own research. And so when you're looking at a wireless propagation channel, you're saying, well, what is the power that I'm getting, or what is the attenuation that I'm getting from a transmit antenna, let's say an access point here in this room, and my user equipment that I'm holding in my hand. Right? This is typically modeled as some form of random process. And I'm walking around, and I'm seeing my received power wobble back and forth. And now we say, well, such a random process, let's call it PRX norm. We said, well, a random process means we have ergodicity. We have some randomness involved in the whole thing. Well, the challenge is that modeling the received power as random is a very convenient mathematical fiction. right, or a very convenient mathematical description method. However, if I say I freeze time, and now I have a completely deterministic trajectory of my UE going through the place, so I have no moving objects, I just have a deterministic trajectory of my UE, then the received power is a completely deterministic process. And I can actually measure on a trajectory in this room here, if everybody else leaves. I can come back tomorrow. If I reproduce that route exactly, then I'm getting exactly the same received power trace that I measured the day before. And because Maxwell's equations are deterministic, the electromagnetic propagation has not changed from day to day. So if I want, how do we normally deal with the randomness? Where do we say that randomness is coming from? Well, we're saying that maybe there are actually other people in the room, or I'm not measuring at exactly the same location, and so therefore now I artificially create an ensemble that pretty much is based on observing at a different time. But strictly speaking, I've created this ensemble not as independent random realizations, because there is no randomness in the received power. I've just said that I'm creating different sample paths by measuring at different time / different space. So in that case, by definition, my ensemble is time. And so in the process of doing my experiment, I am blurring the borderline between what is time and what is ensemble, because the ensemble is time by design of my experiment. So therefore, I enforce an ergodicity on the random process that I'm observing. So some people in the literature have asked the question, well, is, for example, the evolution of power as a function of time an ergodic process or not? And in my take, that is an unanswerable question, because if I create my ensemble as different temporal realizations, then of course it's ergodic, and by definition by construction. But if I don't have another way of creating randomness in my system, well, then that's the only thing that I can do. So I know it's going to be ergodic, but you have to keep in mind that there is not a true randomness in the whole system. And this is something that you have to consider a lot and it goes back to a discussion that we had at the very beginning of this lecture of what is randomness. And even the throwing of the dice, we're saying that, well, it's random with 1/6. Well, if I condition this on the particular physical characteristics of the hand that throws the dice, if I know exactly the movement, if I know the friction of the skin and so on, then that is, then I've got a completely deterministic process. And there might even be people who are so good at controlling how they're throwing the dice that they might make the dice unfair. And so those are things that you have to consider in the setup of your system. That was already for regular sort of just realizations of random variables. When we're now coming to these random processes, that question arises even more. So when you're doing experiments, when you're creating a practical setup, and you're trying to analyze with certain statistical tools, you really have to ask yourself the question, well, where is the randomness coming from? Do I have time and ensemble to be independent of each other or not? Because if they're not independent, then certain questions just become unanswerable. Okay, you're not going to get such semi-philosophical questions on the exam, obviously, but for those of you who will work with random processes in the future, and that's probably more than 90% of you, those are important considerations. So coming back to the categorization of random processes, we were discussing last time about two different distinctions of continuous and digital. One is the process time discrete or time continuous? And the other thing is it value discrete or continuous? And so the typical example would be sampled noise. Right? I can measure some atmospheric noise at regular time intervals, and I just get an obviously time discrete sequence of continuous values. And now, if I measure the amplitude with a finite resolution analog to digital converter, then of course I'm converting then I'm being now at a value discrete realization as well. If I just have, let's say, a 1 or 2-bit ADC, then it becomes very obvious that this is value discrete. If I have a 16-bit ADC, I will probably, for practical purposes, consider it as value continuous, but strictly speaking, it will still be value discrete. Now, one important example that I didn't get to last time is the so-called counting process that counts the number of occurrences that have occurred until time t. So if you're looking at how does that look, it's actually an example of a time-continuous value discrete process. And because I'm saying that, let's say, up to this time, nothing happened. Right? Then I have a jump by 1 because something happened. And I don't know, say you're looking at the number of earthquakes in Los Angeles that happened up to a particular time. And then you get, maybe for a while, nothing. Then you have another jump. Right? And because earthquakes usually occur in bursts, you're getting a whole bunch of them at short distance, one after the other. Then there's a whole lot of nothing, right? And so on. So each of those things here is an increment of 1. Sorry, this, I'm again not drawing very nicely. But the occurrences can happen at any time, potential time t, right? So it's time continuous. We're not just met. If I've rephrased it and said, at the end of each day, count how many earthquakes have happened up to that end of the day, right? Then it would become a time discrete process. But if I'm just saying how many things have occurred until time t, then this is a time continuous process. Now, let's look at how we can do a characterization of a random process in general. And for now, I'm going to revert back to time discrete. So we're saying that for every n that's between 1 and infinity, we take the probability that the sequence xt to xtn is an element of B for arbitrary dimensional sets B, arbitrary n-dimensional sets B, and distinct times. In other words, the joint PDF or PMF, depending on whether it's value discrete or value continuous, right, of all relevant variables that can be countably or uncountably infinitely many. Right? So this is conceptually fairly straightforward. In practice, of course, in the general case, completely unusable. Try to do a 300 million dimensional probability density function, and that's obviously not going to work. So in the special case that the realizations at the different times are independent of each other, and even better if they are IID, then obviously we are in a much easier situation, because then we can just say, well, that just decomposes into the product of the individual PDFs at the different times. But that is a special case. So what is normally done to solve this problem is we characterize only the mean and the correlation function. Now, if you're thinking back a little bit to our discussion of Gaussian variables, you will remember that for that particular special case, characterization of mean and correlation function is actually a complete characterization, which is one other reason why everybody loves Gaussian variables, and it makes life so much easier. If it's not Gaussian, then we're losing information in the process of restricting ourselves to the first two moments. But it is the only way how you can practically have a reasonable characterization. So we're saying we have our mu x of t, which is the expectation of x of t, sorry, xt. And you do recognize, right, that the mean is now potentially a time variant function. And that's very important. That again arises from the fact that for each time t, I'm taking the expectation over the ensemble, and that can change. Right? We were talking last time about having a sinusoid with some noise superimposed on it. Right? So then the mean is just that sinusoid exactly that we were looking at. And we are dealing with the order correlation function, which is for two time instances t1 and t2, the expectation of xt1 times xt2. And by the way, if we're dealing with complex variables, the order correlation function has a complex conjugate on one of those. There are different conventions. Usually it's xt1 star, xt2, but I've seen it flipped around as well. And then there is the auto covariance function, which is just the expectation of xt1 minus expectation of xt1 times xt2 minus expectation of xt2, right, which can be written as the autocorrelation function minus mu xt1 mu xt2. And of course, if you think back about our discussion of two joint random variables, if we, instead of saying we have xt1 and xt2, and we're just saying these are two random variables, x and y, and we want to describe the pair of them, well, we had exactly these equations for it. And so there is relatively little conceptually new. You just have to realize now that, well, really the two random variables that we are picking are our observations in the random process. Let's call this xt1, and here we have xt2. At each of those time instances, we have a probability density function of what we have there, and then we are analyzing the mean and the cross correlation between those two variables. So, going back to our example of xt being the cosine of 2 pi ft plus theta, with theta being a random phase, right? We said that our different sample paths, each of them is a pure sinusoid, but they're all starting out with different phases. And so if we want to now see what are the characteristics of this, well, the expectation of xt, which is our potentially time-varying mean, is now the expectation. And I'm now writing down explicitly what is the expectation over. It's over that random variable theta, right? Over the ensemble of different theta. And cosine of 2 pi ft plus theta, which is integral minus pi to pi of cosine of 2 pi ft plus theta over 2 pi d theta. And so again, I stress there is no integration over time. There's purely an integration over theta, and that of course is 0. By the way, I have to warn you that the nomenclature I'm using here, indicating what the ensemble is over, is not standard statistics nomenclature. So don't get astonished when right, I've had discussion with the statistician and they said we never write this because it's clear that it's the expectation over the ensemble. And I usually say then, yes, but what is your ensemble? Well, the ensemble is the ensemble, but physically speaking, what is the ensemble? And so that's sometimes the communication difficulties between people doing experiments and people doing the math of the probability. So don't insist that this would be the only correct nomenclature. It is not. It is just something that I consider helpful. So it's up to you on whether to use it or not. So if we're now looking at the cross correlation, then we're saying, well, our Rx of T1, T2 is now, of course, 1/2 times 1 over 2 pi of minus pi 2 pi cosine of 2 pi f T1 plus T2 plus theta, T theta plus 1 over 2 times 2 pi minus pi 2 pi f T1 minus T2. Right, cosine, of course. T theta. Right? And why? I mean, of course, you just plug in the definition of xt into the definition of the cross correlation function, and then you're applying the equation cosine alpha cosine beta is 1/2 cosine alpha plus beta plus 1/2 cosine alpha minus beta. And I'm sure you remember that from trigonometry. And so that now becomes 1/2 times the cosine of 2 pi f T1 minus T2. Because that first integral again becomes 0, and because we're integrating over cosine of theta plus some offset over all possible values of theta, right, that always integrates out to 0. That second part doesn't have the theta in it anymore, so now that integral just becomes 2 pi, cancel out this thing here. What remains is cosine of this expression here. Okay, I'm going to give you one more example before we're going on our break. We are looking at a random variable, at a random process, xn being z1 plus zn, n being 1, 2, and so on, with the zi being 0 being uncorrelated and with same variance of all of them. Right? So we could just say, well, they are IID 0 mean with a particular variance, and our z. And then the xn is just the adding up of these different IID realizations up to a particular time n. So now we can look at two different time instances and say, well, let's look at an xm and an xn. We're just arbitrarily calling one of m to be the larger one. Obviously, we can flip it around with 1. And we're saying, okay, what's now the cross correlation between those two variables? So how do we solve this problem? Well, first of all, we're saying, what is our definition of the autocorrelation function? What's the expectation of xn times xm? Now, we can rewrite this as the expectation of xn. And then xm, we said, is, of course, the sum of our zm, which we can now split up into the sum over the first n terms, right, which is, again, xn plus the sum over whatever comes afterwards, right, which is I equal n plus 1 to m of zi. So I've simply reformulated what is my xn here. Please ask if that is not clear, and that is the essence here. So once I have that, I can say, well, linearity, so therefore I have the expectation of xn squared plus the expectation of xn of, times the sum of I equal n plus 1 to m of zi. Right? And expectation of xn squared is, of course, n times sigma squared. This is just n times adding up the variance that we're seeing here. And the second term can now be written as the expectation of the sum of j equal 1 to n zj, right? That's just rewriting again xn, times the sum of I equal n plus 1 to m zi, which is the double sum of j equal 1 to n, I equal n plus 1 to m, times the expectation of zi times zj. So the set of the zi and the zj, of course, is disjoint, because the first one is the first n, the other one is the remainder. So that cross correlation by definition is 0, and that means our final result here is n sigma squared. Now, if we flip around and say n is larger than m, we get, of course, m times sigma squared. So our final result is that our x of nm is sigma squared times the minimum of n and m. Okay, I have one more exercise, but we're really starting to run out of time. So I'm just going to write down for you the problem statement and the solution, and you can work it out in your own time of how you're getting from A to B. And so we have an IID sequence, x, and we're starting with minus 1, that's just for notational convenience, x0, x1, and so on, as an input to a digital filter. And also that sequence has the properties expectation of the xi is 0, and the variance of the xi is 1. And the output of the digital filter is yn, that is xn plus xn minus 1. And the question is, find the expectation of yn and autocovariance function cy of mk. This is, by the way, it seems such a primitive filter, but you would encounter that in practice if you're using, let's say, differential modulation, because you say that what you actually want to send over the air is the difference to the thing that you just sent before. Background for those of you who know communications is that, well, in that case, you don't need an absolute phase synchronization because you only look at phase differences from one time to the next. You don't need to recover the original carrier phase, which is actually a very complicated thing. So this is being used in, for example, Internet of Things modulations and similar things. Okay, but coming back to the abstract mathematical problem, right? This is what you should find out, and it does turn out that, of course, expectation of y I is 0, and the cy of mk is 2 minus absolute value of k for absolute value of k smaller than or equal to 1, and 0 otherwise. Leave you with that. We go on to our break and resume at 9:14. Let's resume. Actually, one last recommendation I forgot in the preparation for exams, or actually for, this is a rule that applies completely generally for studying, right? It's not restricted to this exam, not restricted to this course. And I'm sure you heard it before, but it bears repeating. When studying, turn off your social media. And it's not about how much time you want to spend on your social media versus, or other distractions versus when you're doing the studying. It's the fact that you will not concentrate. And if you are watching this video afterwards, and every 5 minutes there is a ping and there is a message coming in, right, it drags you out of the focus of what you're following along here. And the number of studies that has shown that this is a very inefficient way of learning is legion. And so if you study and turn off the distractions. If you have a break and you enjoy something else, enjoy that something else, but don't mix these two things together. Anyway, coming back to the description of the random processes. Now, let's say we have two random processes, x and y, and we want to find out what is the cross correlation between xt and yt, so between those two random processes. So the definition is very straightforward, right? Our cross correlation function, r of t1, t2, is just the expectation of xt1, yt2, and the autocovariance function, the cross covariance function is expectation of xt1 minus mu xt1 times yt2 minus mu yt2. And notice that when we're dealing with a autocorrelation function, of course, flipping t1 and t2 doesn't make a difference. And whereas when you're dealing with a cross correlation function, it might very well change the result. So consider now the question of what if y is created by sending x through a linear filter with a particular impulse response. We're saying send xt through linear filter with impulse response h of t. So this is a relevant example. And again, that occurs very often in practice. Doesn't matter whether it's communications or control problems, and you experience that all the time. So we will be able to express the cross correlation function in terms of the autocorrelation function of the original process x, right, and some characteristics of the filter itself. So how would we solve this? Well, we're starting out by saying, well, what is our y of t? Well, that is the convolution, of course, between h and our process x. So the expectation of y is therefore the expectation of this thing here, obviously, and we can, as always, interchange the sequence of expectation and integration as long as certain convergent conditions are fulfilled, which of course we assume here. So we have the integral from minus infinity to infinity of the expectation of h of t minus u times x u du. And since h is actually not random, but is a deterministic function, so we just need to place this by h of t minus u times expectation of x u du. And therefore we conclude that our mu y of t is the convolution between our impulse response h of t minus u with the time varying mean mu x of u du. And that's really just a simple plugging into the defining equations. When we're now looking at the cross correlation function, and the principle is very similar. We just need to plug into the defining equation, and so this is the expectation of xt1 times the convolution of. Now we're just writing the convolution in the alternative formulation, and this would be h of u x t2 minus u du, which is integral minus infinity to infinity of h of u. So we again pull the expectation in here, and again the h of u doesn't contain any randomness, so therefore all we need to deal with here is x t1 times x t2 minus u du. And so we can just say that our cross covariance function rxy of t1 t2 is the integral from minus infinity to infinity of h of u times rx of t1 t2 minus u du. Right. So again, it's basically just a convolution expression. You just have to pay attention to the fact that the function with which you're convolving is actually two-dimensional, but the convolution occurs only along one dimension, along the T2. Not terribly surprising, because it's only the y that is actually the convolution of the process with the impulse response of the filter. The x is never, we have no further processing of it, so there should be no special convolving with that. Now, if on the other hand we're looking at the autocorrelation function of y, and so we're looking at the yt1, yt2, then we can expect it's probably going to be some sort of two-dimensional convolution, because now that we're both the first and the second term in this expectation here runs through the filter. And if we write this all down, well, we can say that this is the expectation of integral minus infinity to infinity of h of w x t1 minus w dw. And so this is our yt1 that we've written down, and that gets multiplied with our yt2. And I'm not writing the yt2 down explicitly, I'm just writing it in this form here, and then we will see in a second why. Well, because I can write this now as integral minus infinity to infinity of hw, and again we're pulling the expectation in here. Now we have the expectation of xt1 minus w multiplied with yt2 dw. But this here is just the cross correlation, so the rxy at time t1 minus w, so x investigated at time t1 minus w, with the y investigated at time t2. So that's exactly what we've determined here. And we just, instead of t1, we're plugging in now t1 minus w, but we've already done the work of doing this computation here. And so if we now write this out explicitly, we have the integral minus infinity to infinity of h of w, integral minus infinity to infinity h of u, and now the autocorrelation function of x, t1 minus w, t2 minus u, du, dw. And that's the final result that we can get in this general form. Obviously now we could have a concrete impulse response like a single exponential decay or whatever for these for the h, and we could have a prescribed autocorrelation function of the x, but in its general form this is our autocorrelation function of the y. So you see clearly that running a random process through a filter changes its autocorrelation function. And essentially what you observe here is we are getting a two-dimensional convolution with the impulse response of what we've run this whole thing through. Now, if you think back to your linear systems courses, you will immediately think, well, convolutions are annoying. Two-dimensional convolutions are annoying squared. And so how do we normally solve this in linear systems? Well, we're going to the frequency domain, and we're just dealing there with divisions and multiplications. And this is actually exactly what we're going to do later on. It turns out that the power spectrum of a random process is the Fourier transform of its autocorrelation function. And by making that step into the frequency domain, we are actually going to be able to simplify a lot of our considerations. Right? Just the question of what is the autocorrelation function of simple additive Gaussian noise run through a filter would normally be a rather complicated exercise. The moment that we're going into the frequency domain, we're going to say, well, we know it's basically just the inverse Fourier transform of the filter response. And so these things become much easier there. But before we get into that consideration, we are going to discuss the concept of strict sense and wide sense stationarity. So let's start out with the formal definition. That is, a random process is nth order, strictly stationary, if for n times t1 to tn, all joint probabilities x t1 plus xi, with xi being an arbitrary time shift to x tn plus xi, do not depend on xi. And furthermore, if the process is nth order strictly stationary for every possible finite n, it is strictly stationary. So that is, yes? It can be in principle any order. So this is a very sort of formal description, and let me try to describe to you a little bit more intuitively what this means. So fundamentally, very sloppily formulated, stationarity says the statistics do not depend on the actual time instant at which we start. And so imagine that we are looking at a time sequence, x1, x2, x3, x4. And I decide I'm going to look at the four-dimensional joint probability density function of these four variables. And that is just one of the possible descriptions for this, for n being equal to 4. And so I get a particular PDF, a joint PDF for this. Now what strict stationarity tells us is that if I take this, so let's call it a grid, and I shift it like this, then the joint PDF that I get here is the same as the joint PDF that I get here. And that is the essence of it. I can shift this thing any way that I want, to the left or the right. It's always going to give me the same joint PDFs. Now, very, very importantly, stationarity does not mean time invariant. And I still have time variations. I still have random fluctuations. I'm just saying that the statistics of that whole thing are not changing as I'm moving around. Now, the strict sense stationarity is actually very difficult to verify and to test, and in particular if we're going to larger order of n. Again, think of experimental values and how do we even get sufficient number of realizations of all these joint characteristics. So what is very often used in practice is the so-called white sense stationarity, which says that, first of all, the expectation of xt does not depend on t. So expectation of xt is simply a constant mu. Right? And the expectation of xt1, xt2 depends on t1 and t2 only through their difference, tau being t1 minus t2. So we can write this as a rx of tau. And so we've simply relaxed our requirement now. So instead of saying that all up to nth order with up to n different points here, we have to be stationary, we're just saying that our mean is independent of time and our autocorrelation function or autocovariance function depends only on the time difference and not on the absolute time. One common misunderstanding is that white sense stationarity is order 2 strict sense stationarity. That is not true. Right? So you have to carefully look at the definition of the strict order stationarity, because second order strict stationarity says that we are taking n equal 2 time instances. And so that is in agreement with what we're seeing here at the bottom for the for white sense stationarity. But now we're saying that for 2 time instances, all the statistics, so the joint probability density functions of xt1 and xt2 have to be in agreement. Whereas for the white sense stationarity, we're saying that we're looking at 2 time instances and only at the first and the second order moment. And so again, that distinction between what is the amount of what is happening in the time domain versus what is happening in this case moment domain. Right? The nth order strict sense stationarity says that in the time domain we're limiting the number of samples that we're looking together at to an order of n. But in the moment domain we're looking at infinitely many moments. And in the white sense stationarity, we by definition limit ourselves to 2 instances in the time domain and to 2 moments. Now again, when we're looking at Gaussianity, right, those differences vanish. But when we're looking at general statistics, those differences do not vanish. And so to provide you an example. And so that could be, for example, that could be like a homework example saying that, well, you've got an xn that is Laplace distributed with a parameter square root of 2 for n equal to 0, and it is normal distributed for 0 with mean 0 and variance 1 for n unequal to 0. And so the question is it white sense stationary and is it strict order 2 stationary? So when we're looking at the white sense stationarity, we're saying, well, what is our expectation of n? And that is 0. Independent of time because both Laplace and normal are 0 mean. And that's how we've defined it here. If we're looking at the autocorrelation function, which coincides here with the autocovariance function because everything is because expectation is 0, and then we see that expectation of n and m is 0 for n unequal to m due to the independence. And sorry, I didn't specify this before, that the samples are drawn independently from these distributions. And so, of course, for Laplace it's clear, the n's, for n unequal 0, we're picking independent realizations of the normal variable. And then for all n, the expectation of xn squared is unity. That's just because we picked the Laplace distribution and normal distribution that have the same sigma, so obviously then the expectation of xn squared is the same. Right? So this particular random process is white sense stationary. Now let's look at the strict sense stationarity order 2. And actually, we don't even need to go to different time instances. We can just look at the 4th moment of the xn. So for Gaussian, we know that the expectation of the 4th order moment is 3. If you don't remember that, you can go back. We computed all higher order moments for the Gaussian at an earlier time. And for the Laplacian, we can say, well, the expectation of that, we do a little bit of a trick, is the same as the 4th order moment of an exponential. Why? Because the Laplacian is just symmetric, and it's a single-sided exponential for the positive n and a single-sided exponential for the negative n. We're looking at even moments, so therefore we can just say, well, what's the moment of one part of it? So for this positive value, so what's the fourth moment of an exponential? And again, we computed the higher order moments of exponentials at an earlier time. That was 4 factorial divided by lambda to the power 4, right? Or generally it was n factorial over lambda to the power of n. And so that is, in our case, a numerical value of 6. So now you see higher order moments just for the variable xn are not in agreement. Therefore, obviously, we cannot have strict sense stationarity of order n, because we're saying it has to be up to the nth order. And so if it's not even fulfilled for the first order, as we have here, then obviously it's not fulfilled, period. So let me now come back to the discussion about ergodicity and how that relates to how we can potentially create an ensemble. And so we were previously saying that ergodicity essentially means that the expectation over the ensemble equals the expectation over time. Now, how is that related to White-Sense stationarity? So assume that we have a autocorrelation function R of tau, right, which is now the expectation of xt times x of t plus tau. And so if we're using that definition, sorry, let me actually go back and first write the general definition. And so we are writing our autocorrelation function now in a slightly different form. And instead of saying t1 and t2, we are saying we write it as a function of t and of tau, so that it's the expectation over xt times x of t plus tau. It's just a formal redefinition because we want to separate out what is the impact of the distance between the two times in an easier way. Now, if I am creating a White-Sense stationary process, and by saying that I take here the expectation over t, and so my different starting points of xt plus tau, then first of all, I have guaranteed that this is a function of tau only, because I've integrated out or averaged out my t. So this can only be a function of tau. So this is automatically going to be White-Sense stationary. Right? I'm skipping over the average value now. Let's just think of the zeroing variables. And at the same time, because I'm taking now an expectation over the ensemble of all possible times t, I also inherently enforce ergodicity. So this is, by definition, ergodic, and thus White-Sense stationary. And so if ergodicity essentially tells us that taking the average over time is the same as taking the average over the ensemble, then once I've averaged out the ensemble, there is no basic dependence on the time left, right, on the absolute time, which means this automatically makes this whole thing White-Sense stationary. And so my key point is that you cannot test for White-Sense stationarity in experimental data if you are creating your ensemble through the assumption of ergodicity. And the moment that you do that, you have already enforced White-Sense stationarity, and therefore any test has to give you, yes, this is a White-Sense stationary. By the way, if you're looking at such data, then you will want to use definition of the Rn that is, sorry, actually, let me skip over that point. This is a little bit too fine. But what is important is that we do know that the magnitude of R of tau always has to be smaller or equal of R of 0. And that just follows from Cauchy-Schwarz. We also know that R of 0 is essentially the expected energy. Right? Because
you have 1 minute left.
It's just telling us this is x and the expectation of xn squared, and that is our R of 0. So depending on how you interpret your xn, if you say my x is the amplitude of something, then it means R of 0 is essentially your expected energy. So that's one important property. And if you now consider this equation here, right, you're saying that the cross correlation always has to be less than the autocorrelation at time 0. Sorry, autocorrelation at time tau has to be less than autocorrelation at time 0. However, it does not mean that R of tau does go down monotonically. There are many processes, and wireless fading is just one example, where your R of tau might look something like this. It can take on negative values as well. So all that this equation says is it can never go above this value 1 here, but it can go down, up, and so on. And so if you, for example, define certain quantities like a correlation distance of when the correlation function falls below a threshold of 0.5, you can actually run into a whole bunch of problems because you might have multiple intercept points. And now you have to start defining of, do I take the first one, do I take the last one, do I take the average of these points, and so on and so forth. Okay, with that, we'll wrap it up for today. We're going to continue on Tuesday with power spectra of random processes.